Chemical Bonding 12, Ozone, a case study in resonance. Larger structures and more in-depth explanations of bonding systems often require more sophisticated concepts and theories of bonding. Nature of science. The principle of Occam's razor. Bonding theories have been modified over time. The newer theories need to remain as simple as possible while maximising explanatory power, for example, the idea of formal charge. Here we have an image of the atmosphere, and you can see that it has 3 layers. It's got the troposphere that goes up to about 10 to 12 kilometres. Between 12 kilometres and 50 kilometres away from the Earth's surface, we have the stratosphere, and above that we have the mesosphere. When we talk about the ozone layer, ozone depletion, we are concerned mainly with the events that occur in this section, okay, the ozone layer within the stratosphere. We're not talking about the ozone that is responsible for smog formation that's produced lower down in the troposphere. You can see here the little hill of smog ozone that we produce in the troposphere. It's about 10% of atmospheric ozone. It has harmful impacts, toxic on humans and vegetation, and the high episodes of ozone do occur in urban and rural areas. Then you have far more ozone present in the stratosphere, or the stratospheric ozone. It contains about 90% of the atmosphere's ozone, has a beneficial role. It acts primarily as a UV radiation shield. And some issues with it are that long-term global downward trends of this ozone are quite worrying, especially above the Antarctic. And we still get a hole in the ozone layer above the Antarctic at springtime. There is only one type of ozone though, okay? And it's just harmful or beneficial depending where it is found. Right, let's have a look at the difference between oxygen gas and ozone. Oxygen has a double bond there, and each oxygen has 2 lone pair of electrons. Ozone has, well, depending which oxygen, you see one oxygen has 3 non-bonding pairs. The centre one has a single non-bonding pair, and the one attached to the double bond here has 2 bonding non-bonding electron pairs, and you can see it's a resonance structure, so it would go between these 2. So the bond order of the oxygens is 2 in dioxygen, sorry, and in trioxygen or ozone it's intermediate between single and double. It's got a bond order of 1.5. In oxygen gas, it's shorter and stronger than in ozone. The bond lengths and the strength shorter and stronger. The oxygen-oxygen bonds have the same length and strength in ozone. So despite this image here, the reality is that both bonds are in between a double bond and a single bond. Okay. So they're longer and weaker than in O2, which is a pure double bond. Formal charge is 0 on both atoms in dioxygen. The double bond oxygen is 0. The single bond is -1, and the single and double bond here is +1. The molecular polarity, it's a non-polar molecule with a symmetrical shape, dioxygen, and ozone is slightly polar molecule. It's asymmetrical shape due to the lone electron pair on the central oxygen atom. Okay, the natural formation and depletion of ozone. Natural formation and depletion. Here you have the sun kicking out radiation, infrared radiation, and UV light. In the stratosphere, there's a steady state in the production and breakdown of ozone. In an unpolluted environment, these two processes occur at the same time to maintain a balance in the amount of ozone. So it's constantly being made and constantly being broken down. Step 1 in the formation of ozone. In the presence of short wavelength UV light, oxygen gas breaks down to form reactive atomic oxygen free radicals. Here. And you can see the wavelength of the UV light is below 242 nanometers. A free radical is an extremely reactive atom, and it has this unpaired electron on it. The atomic oxygen free radicals react with oxygen gas to form ozone. This step occurs twice, once for each atomic oxygen free radical formed in step 1. So the overall equation is 3 oxygen gives 2 ozone. It's a balanced equation. The natural depletion of ozone. In the presence of longer wavelength UV light, you see the wavelength is below 330 nanometers. Ozone splits up, or it photodissociates, into oxygen gas and a free radical oxygen atom. And the atomic oxygen free radicals react with another molecule of ozone, forming 2 more molecules of oxygen gas. And so the overall equation is 2 molecules of ozone gas give us 3 molecules of oxygen gas. Levels of ozone remains constant as long as the rate of formation and the rate of depletion are the same. In this way, the ozone layer is maintained. It's able to absorb both short and long wavelength ultraviolet light and protects the Earth from damaging effects of this type of radiation. Bond dissociation, energy and wavelength. Here we have the ultraviolet light. UVA is between 400 and 320 nanometers. UVB between 320 and 290 nanometers wavelength. As you can see, the wavelength decreases as we go from UVA to UVB, and so the energy increases as you go from UVA to UVB. The relative bond strength, as we discussed earlier, oxygen gas has a stronger bond than this intermediate bond in the ozone, which is somewhere between a single and double bond. So the bond dissociation energy, or bond enthalpy, is 498 kilojoules per mole in oxygen and only 363 kilojoules per mole in ozone. This means that the wavelength of UV light that breaks the bond will be different in both of them. It's a more energetic but shorter wavelength of 242 nanometers breaks this bond, and the less energetic but longer wavelength of 330 nanometers that breaks the bond in ozone. Let's have a look at a question here. It says, calculate the wavelength of light with an energy of 3.5 times 10 to the minus 19 joules. Determine which region of the electromagnetic spectrum the light belongs to. We know the speed of light, and we know Planck's constant, and we know this formula. Plug in all the numbers. You've got Planck's constant multiplied by the speed of light divided by the energy given here, and we get 5.68 times 10 to the minus 7 meters. And so we convert this to minus 9, shift the decimal place to minus 8, minus 9. Nanometers is minus 9. So we'd have 568 nanometers. Another example. Example 2. The energy needed to break the oxygen-oxygen double bonds in O2 is 496 kilojoules per mole. Calculate the wavelength of light required to break this bond. Well, the first thing we need to do is to calculate the energy of a single double bond in joules. So there'll be a few steps here. The first thing we need to do is, we know that 496 kilojoules is for 1 mole of bonds. Okay, so we need to find out how much it would be for 1 bond, and we know that 1 mole is 6.02 times 23, so we're going to use this conversion factor to convert it into what it would be for 1 bond. Then we've given it in kilojoules, but we need it in joules, and so we can use this conversion factor here, where 1 kilojoule equals 1000 joules. You do the math, and you get 8.239 times 10 to the minus 19 joules. Now we have this, we can use the formula we just used before. Planck's constant multiplied by the speed of light divided by energy gives us wavelength. And you can see again our answer comes into minus 7 meters. And so we can convert by shifting the decimal place 2 along to minus 9 and put it in nanometers, which would be 241 nanometers. Another one. Ultraviolet light with a wavelength of 330 nanometers breaks the oxygen-oxygen bonds in ozone. Calculate the bond dissociation energy for this bond. So first step, we calculate the energy to break 1 bond. And we have the wavelength, so we can use this formula here. We can rearrange the formula and just plug in Planck's constant, the speed of light, and the wavelength given in the question, which is 330 nanometers, and that converts to 3.3 times 10 to the minus 7 meters. And then we calculate the energy per mole. Okay, so we've got 6.027 times 10 to the minus 19 joules per bond, and we're going to have 1 mole of it, so 6.02 times 10 to 3 bonds, and that gives us 3.62 times 10 to the 5, or 362 kilojoules per mole. Okay, the catalysis of ozone depletion. Let's have a look at this. If you recall the natural cycle, we had ozone and oxygen in equilibrium, and the ozone being broken down and being formed constantly. The rates of the dissociation and the formation reactions of ozone are the same under natural conditions. Chlorofluorocarbons, or CFCs, and nitrogen oxides, NOx, from human activities act as catalysts in the destruction of ozone. So the depletion gets larger than the formation. The chlorofluorocarbons, this is the mechanism. First step is the photodissociation of CFC produces a very reactive free radical chlorine atom. And you can see here we've got trichlorofluorocarbon in the presence of UV light, breaks down into a reactive free radical and kicks off a very reactive chlorine free radical. The carbon-chlorine bond is weaker than the carbon-fluorine bond, so a chlorine atom breaks off instead of a fluorine. Step 2, the free radical chlorine atom catalyzes the decomposition of ozone. So the ozone and the chlorine, or the free radical chlorine, react to give oxygen and this chlorine-oxygen free radical. A free radical oxygen atom in the stratosphere then reacts with the ClO free radical, forming more free radical chlorine atoms. A single chlorine atom can destroy thousands of ozone molecules. And so you've got the oxygen free radical reacting with the chlorine oxygen free radical to give oxygen and another chlorine free radical, which can then go on to react with another ozone molecule. The overall equation for the depletion of ozone by free radical chlorine catalyst is ozone plus 1 oxygen free radical in the presence of a chlorine free radical gives 2 oxygen molecules. And you can see this remains here. It's not part of the equation because it's acting as a catalyst. Nitrogen oxides formed by the reaction between nitrogen and oxygen gas that occur in the high temperatures of jet engine internal combustion engines. Nitrogen oxides may catalyze the breakdown of ozone by different mechanisms. Here's one below. Nitrogen oxide reacts with ozone to give oxygen and nitrogen dioxide. The nitrogen dioxide that forms reacts with oxygen-free radicals in the stratosphere. And then you get nitrogen monoxide again and oxygen formed. If we cancel those nitrogen dioxides out, you can see the overall equation for the depletion of ozone by a nitrogen oxide catalyst is as follows. You've got the ozone and you've got the oxygen-free radical giving 2 oxygen molecules in the presence of this nitrogen monoxide, which is acting as a catalyst. And that's the last slide. Okay, goodbye.